The other day, I opened up an IRB console and I ran this command. And what's cool about Ruby's number underscore notation is that we can see just how big this number is. 1 billion times object.new. And I'm a little impatient, so I was doing other things on my computer while this was running in my IRB console. And after about 2 minutes, uh, it came back, it completed no problem at all, which is crazy if you think about it, because each of these objects I was creating, and we'll get more into this in a bit, are 40-byte objects, and there were 1 billion of them, so that's 40 gigabytes. For context, I ran this on a machine which has a total amount of memory of only 16 gigabytes. How did this happen? Well, Ruby has a garbage collector, right? We know that. We know we can run commands like that, however outrageous. Maybe if you're a little more patient than me, you could do 10 billion or something like that. And the garbage collector will take care of it for us. And just to clarify, when in this talk, I'm talking about Ruby's garbage collector, I'm talking about CRuby, not JRuby or Truffle Ruby, which all have really interesting garbage collection algorithms too. But just wanted to clarify, this is CRuby, MRI Ruby. If what I just said doesn't make sense to you, don't worry about it. It's just the Ruby you're familiar with. Back to our billion objects, though. Ruby's garbage collector took care of this because we didn't keep a reference to them, right? We didn't set it to some variable. We didn't ask Ruby to remember this for us in any way, so it just collected them as it was creating them, and it didn't blow up my memory in any way. I could work on other things while it was happening. And we'll get into exactly what GC stat does later in this talk, but just to confirm, we can actually see with this GC stat count command that GC ran over 50,000 times, which is pretty neat to be able to see and confirm for ourselves what exactly was happening that let me make these billion objects willy-nilly on my computer. And also we'll get into what pages mean, but for now it's just a proxy for how much memory we were using, and we can see the memory we were using didn't grow at all really from before we made those billion objects to after. So as our buddy Oscar the Grouch from Sesame Street, who lives in a trash can, will tell us, kind of go away, right? Ruby does GC for us. It deals with our trash. The whole point of having a garbage collected language is that we as developers don't have to worry about it, right? Except, and I know this is a big slide faux pas to have so much text, but this is, you don't have to read it for now. This is from the Ruby 3 release notes, which came out in Christmas of last year. There was a little section about GC, and at the end of that section, it said, please test first, which is great, except in order to test first, we have to actually know what's going on here. So what was happening? Thanks so much for coming to this talk, a day in the life of a Ruby object, or better yet, a day in the life of a billion Ruby objects. I hope it does a lot of things, and we'll get into the goals in just a bit, but one thing to really note is please definitely feel free to work along as I'm doing this. There will be a lot of stuff from IRB consoles, and I hope you just open one up and play with it as it's going, as a way to learn for yourself too. So my biggest goal here in this talk is that by the end of it, we'll all be able to conceptualize GC-related issues. So in a similar way to how you might see some issue and think, that's in the realm of a networking issue, I hope that by the end of this talk, you'll be able to see a scaling or tuning issue and know it's related to GC in some way. And more specifically, that we'll all have a broad understanding of how GC works, of what exactly it's doing. And in order to get there, the goal is that we all will understand the arc of object creation. So what's happening when we do those object news? what is the garbage collector actually doing, all of that information. And a little more about me. I sometimes wear a colorful bucket hat when it's raining. More relevant to this talk, I'm writing a book about Ruby GC at the moment. I really enjoy writing and writing about Ruby. I'm also a Ruby blogger. I write the tip of the week in Ruby Weekly, and I have some experience as a backend Ruby developer. And also, while I have your attention, I am one of the co-organizers of a new Ruby group. It's a women non-binary group. We have 2 speakers a month. We would love, if you identify as women non-binary, for you to join us. We'll always have the latest meetup details or the next one pinned if you check it out at that Twitter. Please register. Please come join us. By the time this talk comes out, the first one will have happened. Second one will be on April 27th at noon Eastern. Please join us. But to get back into what we were looking at, so if we were looking at those release notes, they said, please test first. If we read a little more, it's asking us to look at compaction and what happens here. So if we go back to release notes about compaction from Ruby 2.7, there are a whole bunch of terms in here, which if we were just ignoring garbage collection and didn't understand what was going on, there's little to no way we would know what any of these terms mean. Things like memory space, copy on write friendly, memory fragmentation, major collections, compaction, pages, the heap. We'll get into all of this through the course of the talk. And as I was saying, one of my goals is really that we all come to an understanding of what each of these terms mean. So instead of focusing on our billion objects, just for now, we're gonna find it a little easier to focus on one specific object. And again, please open up an IRB console, pause me, rewind me, do whatever you need. I think this will be more impactful if you learn alongside me. So let's see what's happening here. When we create a new object, we get this object back, and we get this memory address. Yours should look slightly different to mine if you're playing along. And we'll get into what that memory address means. But first, kind of how can we access the object? Well, we can't. We haven't made a variable and assigned it to that variable or put it anywhere that we'll be able to access it. And that was what happened with our billion, right? So then they just got cleaned up. If we wanted to do that, we could say obj equals object.new, and then we'll be able to access it. Some of us might be familiar with object ID, which is a unique identifier that we'll get into per object. But if we want to drill down to what the memory address is actually saying, we have to get into a bigger picture of what's going on with memory generally here. And so your machine has some operating system heap, which is most of its memory. And any machine you're running your Ruby code on will have this kind of big memory store. And within it, obviously not to scale, will be a Ruby heap. It's going to feel like turtles kind of a little way down. And what we're looking for here is where our object is going to live. And this Ruby heap can sometimes have references, we'll get to this, to the operating system heap. It can sometimes change size, so it can sometimes grow. It can ask the operating system for more memory. This is where you might see your Heroku dynos are showing you that they're consuming more memory as your heap is growing. It can change size. And if we drill into the Ruby heap and see what's going on in there, what's happening at the object level, we'll see that the Ruby heap is actually made up of these units of memory called pages. So when it asks the OS for more memory, it asks for them in increments of pages. And drilling into a page, each page has about 409 of what are called slots. It's about 16 kilobytes in size. And we finally reached here with the slots where we'll actually store the objects. These can be empty, unallocated slots that don't have objects, or they can also contain RVALUEs within them. The slots are all a fixed size, and that's that 40 byte size that I mentioned earlier. So slots can be, the page also has a header with some information about the overall page and also about some information about each slot within that header. And then, like I was just saying, some slots can have these R values, which are, you can just think of as, they're like Ruby's internal C representation, a Ruby value of an object. And that's where the objects themselves live. So when we made our new object, we can think of it as existing within this R value. And those can be objects or any types of objects. And there are some cases like this long string. I just wanted to give myself a tongue twister to say. So supercalifragilisticexpialidocious, which doesn't quite fit in the 40 bytes, right? This string is, as I've tried to demonstrate with it going over the border, it's too big for the R value space. So what'll happen in some cases like this is we'll actually have the R value point to some external memory address, and that memory will be in the operating system heap itself. So when we were looking at memory addresses of objects earlier, each R value has its own memory address, and then within the R value, we can reference some memory address sometimes outside in the operating system heap itself. What's important to note here is this means that sometimes our Ruby heap can be smaller than the amount of space that or can have less memory than our entire program is actually taking, right? So I just wanted to be explicit about this because sometimes you'll see different metrics here, right? Where the size of your Ruby heap isn't actually representing the same memory consumption you're seeing on Heroku or AWS or wherever. And I wanted to go on a fun little aside about strings here, about when they'll be too big for R values. In order to do that, we're going to have to create strings of different sizes. So if you're following along in a console, this is just a little formatting. If we use this %.d syntax, we can turn an int into a string, and more explicitly, we can make a string of a certain length from an int. So in this case of 23 characters. And so in this, I'll use the red underline throughout as just like where to highlight in lieu of a pointer. In this red underline, we can see what we're doing is saying for each of those million times, create a 23-digit string representation of that number. And we did that for 23 and 24 strings. What's really cool here, 23 and 24 characters, sorry, 23 and 24 length strings. So 23 and 24 characters are exactly the boundary of when the string is stored within the R value and when it's stored externally. And we can actually see this difference in processing time. So we can see that to create a million strings of length 24 takes almost 10 times as much time as to create a million strings of length 23. This isn't necessarily practical. No need to go adjusting your strings. I doubt you're making millions of them. Just was more meant as a cool demonstration of how we can create little snippets to see what's going on with garbage collection itself. As you're playing along, go ahead, play with 22, 21, 25, kind of see that boundary clearly for yourself. It's pretty neat. And just while we're on the aside, the way I got those processing time measurements was IRB has this measure command. So if you just type in measure, you'll see the processing time for any future command you write in Ruby 3. So back to our R values. R values can also hold references to other R values. So in the case of an array, for instance, if we had our object within an array, what'll happen here is this R value will have a reference to another R value where our object lives. And we can actually see this within Ruby itself. So object space is another name for the Ruby memory, and we can require object space, load in that standard library, and use object space.dump to see data about our object, it'll give us a JSON representation of memory. So we parse that and we get it neatly. And so yeah, in this case, we're doing object space.dump. We can dump the array from earlier and get its references. We'll get more into what dump is doing and more information it's saying, but for now, arrays will in their dump contain references. And we can see the address of that first thing in the first element in the array and confirm that it is in fact the exact same address as our object outside the array, right? So it's telling us where the R value is that's storing that object itself. Okay, so that was a little zoomed in. If we zoom out a bit and try to think again about our billion objects and how on earth that happened, we know in order to create objects, we needed to have some sort of page. We now know this in our Ruby heap. And the page had some R values in it, right, to represent all of the billion objects we were creating. But since there were a billion, we might have needed a few pages and a few slots, but probably a few R values, probably more than even that. But we know I didn't run out of memory, right? We know I didn't actually have this situation where there was a crazy huge Ruby heap that was flooding the operating system heap and more. And why not? It's because Ruby uses this tricolor mark and sweep algorithm to do its garbage collection. So let's walk through exactly what that algorithm is doing. So these are the steps here, and we'll go through them. No need to memorize this. This slide will come back up quite a few times. But we first mark all R values white, and then the next step is to mark all root R values gray, which begs the question, what is a root R value? Root R values are R values that the program will always know about that are vital to the running of the program. And we always start here in our algorithm because anything not reachable from here will be collected, right? Anything we need to run our program is going to be reachable in some way through references from this root R value. So in order to understand, and roots, examples of roots are VM, finalizers, machine context, global list, all those sorts of things. And we can dig more into that maybe in Q&A if it's interesting or something like that. So in order to illustrate our mark and sweep algorithm, I've created a few root R values, which we can move to the top of the screen to make room for a whole bunch more R values that aren't roots. These arrows represent references. So like we saw in the array referencing another R value, that's what the arrows represent. We have some cases here where root R values reference other R values. We have some cases where non-root R values reference R values. We have some R values that just don't have any references. And so this should give us a pretty clear understanding of what's happening. And we'll walk through the algorithm. So the first step is to mark all R values white, which we've done. It's called the tricolor mark and sweep. It's really like tri-shade of gray, but that's okay. So we've marked all R values white. Next thing we'll do is mark all root R values gray. Okay, so that's our 3 roots at the top here that we can mark gray. Our next thing is a little while loop. So while there are gray R values, okay, pick a gray R value. Okay, we'll pick this one. Mark all R values it references gray. Great, that's just the circled one, or they're all circled, the thickly circled one. And then mark the original R value black. Okay, done that. While gray R values, pick a gray R value. Next one, mark all the R values it references gray. Great, mark it black. Okay, keep going. Pick a gray R value, doesn't reference anything, mark it black. pick a gray R value, mark all the R values it references gray, mark it black. Keep going, gray, no references, black, gray, no references, black, gray, no references, black. And we've now finished our little while loop, right? There are no more gray R values, which means we only have black and white R values. And at this point, we can say that all of the white R values can have their slots reallocated. So those R values, we have absolutely no way of reaching from the root, right? They're irrelevant to our program. Our program doesn't need to remember them to continue executing, so we can make use of their memory for something else. We can get rid of them. And so what was happening with our billion objects is we had a page, we had all these available slots, we filled it with R values, the garbage collection ran, it looked at all these R values, it said, hey, none of them have any references from the root pointing to them. We don't need to remember them. Let's forget about them. All of those slots can become available for new R values. So fill them up again with more R values. And so if we look at this on a broader scale, what was happening was we had R values in our heap that were filling a page. When we needed more memory, garbage collection ran, it cleared out this page, said, hey, all of these slots are up for grabs. More R values would fill them out, and this cycle would repeat over and over again. And like we saw earlier, it repeated up to 50,000 times. Or over 50,000 times, forgive me. Which is really, really cool. This algorithm is super interesting. One thing to note here is that it's tricolor, right? We are using gray, and you might have the thought, why not just black and white, right? Why do we need this intermediary step of marking things gray? Well, it's actually really interesting. Ruby's garbage collection is what's called Stop the World GC, which means it pauses execution of our programs to do garbage collection, to run through this algorithm. So if you imagine your program executing, you can think GC is fully pausing this, and that's actually quite a long pause, right? You could imagine for a really long program, this pause could get pretty long and debilitating. But what the gray allows us to do is pause our garbage collection. So it allows us to keep an intermediary state. We can look at this kind of picture of black, white, and gray and know where we need to pick up and where we've already looked. Whereas if it were just black and white, we wouldn't have this option available to us. So this is what incremental garbage collection is, which is a term you may have heard. It lets us do these short GCs as our program is executing, as opposed to longer ones, and kind of pick up where we left off. To go back to our object, as we said earlier, we're holding a reference to it now, right? So it won't ever be collected until we clear that reference. But that kind of begs an interesting question here. What if we create our object, and then we did this billion times object.new, and then obviously we haven't done anything with our object, so we want to look at it again? What would have happened to our object in that time? Was each of those 50,000 something garbage collections looking at our object, right? That seems very inefficient for it to have looked at it 50,000 times for nothing to ever change. Which brings us to something, another strategy Ruby's garbage collection employs called generational garbage collection. And this is built on the weak generational hypothesis, which sounds fancy, but is basically the concept that most objects die young. That most of the objects we create, and we can think of this in our Rails apps, there are lots of parts that are transient, won't last for a while, right? So creating a web page needs a whole bunch of objects, but once we've returned a web page to a client, we don't need those objects anymore. But there are other objects that may persist, like a user or a session, through the longer journey of a program. Okay, so most of our objects are dying young, so generational garbage collection is gonna take advantage of this. And garbage collection, as we've discussed, will run by itself, but we can also manually trigger it with GC start. And GC start actually takes an optional parameter of full mark, which can be either false or true. So what's full mark? Well, it's whether or not it's going to look at every object. So full mark false is only going to look at young objects. And this is actually called a minor garbage collection. And then full mark true is going to look at all objects, which is a major garbage collection. So Ruby has two different concepts: minor garbage collection, which looks at fewer objects and runs more frequently, and then major garbage collection. There are a few things that trigger major garbage collection, but mostly it runs if the minor garbage collection hasn't freed up enough space. So the minor will go first, and then if your programs or our program still needs more space to execute, major will then look at all objects as opposed to just the young objects. And we can see this in practice. So if we go back to our GC start, a brief aside about me: I lived in Boston for a few years. And if you know a Boston accent, or if you've seen Good Will Hunting or anything like that, in Boston, they like to drop the R often. And if we drop the R when we say start, we'll be left with GC stat, which is a bad joke, and also exactly how we can see information about what the garbage collector has done. Feel free to run this in your console. It's a lot of different things here. Many of them are really interesting. We can dig into more of it in Q&A. But relevant to us right now are these two: the minor GC count and the major GC count, which are telling us how many times minor GC ran, like the names imply, versus major. And something neat here, if we look at our billion object creation, and instead of just doing GC stat of overall count, we segment it into minor GC count, we'll see that the vast majority of the GCs that ran were minor. In fact, only 4 of them were major. And what's more, those 4 majors just ran on IRB initializing. So when IRB booted up, it ran 4 major GCs, and none were run in the creation of our billion objects. And just to confirm for ourselves further, there were only a handful of minor GCs before those billion objects were created. Again, play around with this yourself. It's really fun. Okay, so what was happening here was the object actually became old really quickly. So instead of looking at it 50,000 times, we barely looked at it at all, which begs the question: when did it become old, and how do we know that? We can actually see age on an object. If we go back to that little dump method we wrote earlier, dump is giving us all kinds of fun information. We'll skim through some of it. So the address, which we can see is the same as above, the type, the class. What's neat here, if we know the class of our object was object. If we dump the object class and take the address of that, we'll see these two addresses match. The size we know from earlier is 40 bytes. And these flags. The flags are where we'll actually be able to see if our object is old or not. If it is old, it'll have this old true flag. If not, it won't have an old flag. So we can define a little old method, which just looks at that old flag if it exists. And then we can define this little count GC until old method, which is creating a new object, starting the GC count at 0, running this GC start while our object isn't old, and then will give us our overall GC count. And we can see that it takes 3 GCs until an object becomes old. Which, looking back at our R value, the age is actually stored on the R value itself in 2 bits. So we're going to do a little bit arithmetic here. It starts as age 0 when the object is created. And then if we run GC start, it'll increase to be 1 generation old, 2 generations old. And once it's 3 generations old, or taking up both of these bits, then we only look at it again in major garbage collection. So at the beginning of the talk, what we were looking at from the Ruby release notes was to do with compaction. And I want to get into compaction a little more from those initial slides. Kind of at a broad level. So if we go back to our picture of our Ruby heap, which we're now familiar with our pages in here and slots, remember about 409 slots per page. If we look at a really contrived example here of R values filling out those pages, we'll see that they're pretty sparse in here. And this is called memory fragmentation. This state, it's our R values are fragmented, right? They're not bunched up together. And memory fragmentation can cause high memory usage and degraded speed. And compacting the heap, which we're about to look at, causes us to use fewer pages and makes the heap more copy on write friendly. So that allows us, when we have to copy memory for multi-threaded programs, or to write memory into forked processes, we have fewer unused copies in these cases, and we can get more into this in the Q&A if it's interesting. It also allows for easier CPU cache hits and all sorts of things. And so the compaction and the algorithm for here is also pretty interesting. We're not going to get into it today, but there's some great talks out there on this algorithm if you want to know more. That algorithm will take these fragmented R values and pull them all into 1, or however many pages they take up, in this case, 1. And back to our console, because we've been so enjoying playing around there, we can actually see the memory address of our objects change. Again, if we create a pretty contrived example here, we can create, say, 10,000 objects in an array, make a new object, and then clear that array, so we no longer have any references to all of those 10,000 objects, and run gc.compact. We have to manually compact, or we can toggle auto compaction on Ruby 3. If we run gc compact, which is available from Ruby 2.7 onwards, and then look at our object again, we'll see that the memory address changed. If you look at the first one, it's this 1A67 and the 1A67D0, and the bottom is this 039370. And so if we go back to our kind of from our intro sequence, this slide about compaction GC, we now see that we actually understand what it's saying here. This release introduces compaction, which can defragment a fragmented memory space. Okay, memory space is that heap, the object space we've been talking about, the Ruby heap. Some multi-threaded programs can cause memory fragmentation, which we've just talked about, leading to high memory usage and degraded speed. The GC compact method is introduced for compacting the heap. We know what that is too now. This function compacts live objects in the heap so that fewer pages may be used. Again, we know what pages are, and the heap might be more copy on write friendly. And we just talked about what that means. And then going back to our Ruby 3 release notes, it's just saying auto compaction has been added to control when compaction runs. We know what that is. Compaction will occur during major collections. Again, we've now learned what major collections are. please test first. And we're much more equipped with our understanding of what this is to be able to test and see what's really happening as we run auto compaction. And just to recap all the things we've discussed up until now, we went through the structure of the Ruby heap. We went through those diagrams with the tricolor mark and sweep algorithm and learned what that algorithm was doing. We talked about incremental GC, generational GC, and now finally compaction. And I just wanted to really thank you for listening to this talk. It's certainly been a pleasure to make these slides and give it. If you've made it this far, chances are you'll enjoy the book I'm working on about Ruby garbage collection. You can drop your email address at buttondown.email/Jemma Issroff, and I'll send you updates as I have blog posts about the book. Speaking of, I'm also working on a blog post series around garbage collection that you can check out at jemma.dev or find me at Jemma Issroff. Definitely, I would love to have conversations with you and continue discussing these things. We can do that on Twitter, on Discord, wherever you'd like. And again, really thanks for listening through on this talk. I hope you enjoyed it.